In this video, we are going to talk about Fourier Transform. Fourier Transform is something really amazing. It is used in diverse number of fields, from image processing to 5G technology. You find it everywhere. But what is Fourier Transform? Any function can be represented in terms of a combination of different sinusoidal waves. And Fourier Transform is a way to represent any function or break it apart in terms of those sinusoidal waves. But why do we need to convert a function? Or to decompose a function into its sinusoidal components? What are the advantages of that? Well, you are able to convert a time domain signal into frequency domain, and you can perform all sorts of operations over that. You can remove the frequencies, you can add frequencies, you can combine and play around with signal in different ways and then convert it back into the time domain, so it is pretty useful. Now moving to the part where it gets really interesting. How are we going to do that and reach this magical formula? I'm going to explain it visually rather than deriving it mathematically. I have created some simulations to do that. I want you to have an intuitive understanding of it. Eventually, we are going to reach the mathematical formula too. Okay, so let's start. First of all, suppose we have any function and we know that it is a combination of different sinusoidal waves. Like in this case, the function is just a combination of a 3 Hz cosine wave and a 4 Hz cosine wave. But how are we going to detect those sinusoidal waves which are present inside that function? In order to detect sinusoidal waves, what we need to create is a wave detector. To create such a wave detector, let's first discuss about a very interesting thing about sinusoidal waves. When you multiply two sinusoidal waves having different frequencies, time instant by time instant, and then add the results or integrate them from -infinity to +infinity, then what are you going to get is essentially nothing. It will be zero. It happens because over the long range, the positives and negatives are essentially going to cancel out each other. It is that way. When the frequency is same for two sinusoidal waves and we repeat the same process, we multiply them and then add or integrate it, you get infinity. So when the frequency is different, you get zero. But when the frequency is same, you get infinity. So if I keep one sinusoidal wave as it is and I have another sinusoidal wave whose frequency I can vary, and I just increase its frequency from 0 and keep on increasing it and then perform this operation of multiplying and integrating every time, I will get 0 value for all those possible values of frequency except when my frequency will reach the same frequency as that of this wave. I know you can see slight rise in values and not zeros at some points. It is happening because my waves are not infinite in this simulation. We will discuss it again later. But when my frequency matches, bang! We are going to get an infinite value. Well, again, it is actually not infinite because again, the waves are not infinite. So overall, this property can be used to create our wave detector. All we have to do is start from a zero frequency, but mathematically we can also have negative frequencies. But for simplicity, let's start from zero frequency and we move towards infinity. And we perform this operation over and over again, multiply, integrate, multiply, integrate. Whenever you find a matching frequency, you are going to get an infinite value. So for all the frequencies where we get infinite values, all those frequencies are present in the signal. This is our wave detector. It's pretty simple, isn't it? Yes, I see that look on your face. Infinity is not very easy to handle, especially in our computers. So in practical applications, we have a finite signal. And when we use our wave detector, we don't actually get infinity, but spikes or sharp impulses. Also, for non-matching frequencies, now our wave detector does not get 0, but some small values. But we have to live with that. This is why you saw those small values earlier. So, let's write this wave detector in mathematical form. Suppose the frequency is f. We multiply function xt by cos of 2 pi ft to perform the multiplication operation. Then we integrate it from -infinity to infinity to carry out our add operation. We will get our expression for frequency domain representation. We will be able to get peaks where frequencies are present in this expression. To deal with the infinity problem, we can integrate it from t1 to t2 rather than from -infinity to +infinity. Oh, I know there is one more problem over here. The problem is that we have not taken phase into account. We just increased the frequencies and assumed the phase will be same for both the sinusoidal waves. But suppose my signal was having a phase difference of 90 degrees. Then the waves will cancel out each other even when the frequency is same, and we are going to get 0. So essentially, we are not able to detect a frequency even when it exists just because of the phase difference of 90 degrees. How are we going to deal with this problem? This is where Euler helps us. So we need one more component, which is 90 degree phase shifted. sinusoidal wave, which is a sine wave. So now you have a cosine wave, and you also need to multiply our signal with the sine wave component, and we combine these components using the Euler's formula. The contribution of the cosine component will be maximum when the phase is 0, and the contribution of sine wave or the imaginary component will be maximum at phase 90. After taking this imaginary component into consideration, our multiplication factor changes to cos 2 pi ft minus j times of sine 2 pi ft, minus because we decide to move in reverse direction in phase. So this now becomes e to the power minus j2 pi ft. We take this and then integrate it over minus infinity to infinity, and this is essentially what Fourier transform is. One more thing needs to be mentioned, that e to the power minus j2 pi ft has the magnitude of 1 at every instant. But when we integrate, all those 1s will add up. So if we integrate from t1 to t2, we multiply the function by t2 minus t1. Our amplitude spectrum is sort of magnified by this factor. This thing can become quite important when you look at some of the variations of Fourier transform, like discrete time Fourier transform or discrete Fourier transform. But if you understand what we just discussed, you can figure out why those factors are present in those equations. I'm not going to go into details in this video to prevent it from being too lengthy. So this is what Fourier transform is. So we have reached the formula. We have derived the formula not by performing any kind of mathematical analysis, but just by understanding the basic theory or intuition behind it. This is what we are going to do on this channel. I hope you got something out of it. Thanks for watching.